It's a pleasure to introduce Dmitry Kerner again. He is a professor in the university that he is a professor, and he will talk about block diagonal reduction of matrices over commutative rings, the composition of modules, effectives of modules, versus the composition of their support. Thank you very much, Dmitry, for accepting the invitation. And you can start when you are ready.
Thank you very much for the introduction. It's always pleasure to speak. So let me, okay, just do you, is it seen what I'm presenting? Yes, the PDF, the slides?
Okay.
Yes.
Okay, good. So I will speak, this is some old work with Viktor Vinnikov. Yes, he's from Beersheba. He was my host when I've been a postdoc there back in 2010, even 2009, 8. So it is about matrices. It is sort of commutative algebra, but I hope it is useful also for singularities of matrices. Yes, the topic which was under investigation in the framework of singularity theory during the last 10, 15 years. So let's begin. By the way, so please do not hesitate to interrupt me at any point, at any step, because I tend to work over commutative rings, and I know people in singularities prefer to work with matrices of analytic functions. So if anything is not clear, please don't hesitate to interrupt. So let me start from the very beginning, from the first year of undergraduate. Suppose K is a field, yes, and A is a square matrix, and then we take the characteristic polynomial of a square matrix. Yes, here it is, as in the first year. And then we can try to diagonalize, or at least to block diagonalize. So suppose the characteristic polynomial factorizes, yes, into some polynomials, and we assume they are co-prime. And then the first theorem of diagonalization is that by conjugation, we can bring a matrix to the block diagonal form, where the characteristic polynomial of each block is exactly this PJT. Yes, these are the factors. And this transformation is done by conjugation. This is the first part. Yes, then we do the second step. If the field is algebraically closed, then this polynomial actually splits into linear factors, or maybe powers of linear factors. Yes, and then A admits the Jordan form. Once again, by conjugation, yes, A goes to U times A times U minus 1. And this result is of key importance in linear algebra and in other topics, in other branches of mathematics. Well, and this is the case of constant matrices. Yes, these are matrices of constants, so matrices over fields. What about matrices of functions? Yes, matrix, say, of polynomials or of analytic functions. So let me formulate the question. We have a matrix. Now it is not necessarily square, just a rectangular matrix. We will always assume that M is less or equal than N. Yes, so there are the number of rows is at most the number of columns. And the entries of this matrix lie in some commutative unital ring. Now, the main rings which are probably of interest for you, these are, say, ring of polynomials, or ring of just formal power series, or maybe a ring of locally convergent power series. Yes, here K is an ordered field. For example, real or complex numbers. Or maybe the ring of C-infinity functions on some open subset of RP, and many other rings. And we consider matrices with entries in such rings. Yes. So hopefully there are no questions up to now. Or once again, is the presentation clearly seen? Yes, can you see the slides?
Yes.
Yes.
Good.
we do.
Okay, good.
Okay.
So these are the matrices, and we introduced the left-right equivalence. Yes, previously it was u and u minus 1, and here there is u and v minus 1. Yeah, so u is locally invertible, v is locally invertible. Yes, GL, GL. Just these are not matrices over a field, these are matrices over the ring. And of course, this equivalence, it is much weaker than the conjugation. Yes, usually in the classical linear algebra, with such an equivalence, we immediately get the Gauss normal form, and that's it. It's not so interesting in the classical linear algebra. And when you work with matrices of functions, then even these equivalence is rather interesting, and the questions are rather non-trivial, even for such an equivalence. And then the question is, when can we bring a matrix to a block diagonal matrix? Yes, this is the most basic and natural question, and maybe even to the fully diagonal matrix if we are lucky enough. And surprisingly, this question was not quite addressed, maybe because it is non-trivial, not an easy question, or maybe because once it was not interesting. So let's see, first of all, the little thing which is known, or the main thing which is known, is the Smith normal form, which is very classical. And the theorem reads, so any matrix over a principal ideal domain admits the diagonal reduction. And so explicitly, if the ring is a principal ideal domain, I will give examples in a moment, and then we have some matrix over this ring, then by multiplication on the left and on the right, we can bring the matrix to a diagonal. Yes, now the matrix is not necessarily square, it is rectangular, so maybe there are more columns than rows, then we will have here columns of zeros. It happens. And an additional little piece is that even the entries on the diagonal, they are decreasing in the following sense. So the ideal generated by lambda 1 contains the ideal generated by lambda 2, and so on. We can arrange, in a simple manner, these entries in a non-increasing way. Now, examples of such rings when this is possible are, yes, the most simple rings, say polynomials in one variable, or power series in one variable, or locally convergent power series in one variable, or maybe polynomials in x and 1 over x, and each time it is just in one variable. Now I will just remark that here, when we speak about analytic locally convergent power series, then the Smith normal form is related to Birkhoff factorization theorem. Yes, it is about half of the factorization theorem. And it was independently rediscovered many times during the 20th century. Now, geometrically, these rings, they correspond to basically one-dimensional varieties, so one-dimensional schemes, if you prefer. Yes, so if R is one of such rings, then spec of R is either just the affine line, or maybe an affine subset, so an open subset of this affine line, or it could be the germ of a smooth curve. Yes, and usually in singularity theory, the germ of a smooth curve is not something very interesting. And once again, every time it is of dimension 1 geometrically. Now let me give interpretation in terms of modules and sheaves. So consider A as a morphism of free modules. We have here the free module, the direct sum, n times the direct sum of with itself. Yes, and here R to the m, and A is a morphism. Yes, just as in linear algebra. And then we get the co-kernel, yes, which is the co-ker of A. This is its definition. And this is a module over R. Yes, any finitely generated module can be presented in this way. So you can think in the language of commutative algebra that we are speaking about modules over a ring. Or if you prefer algebraic geometry, you can think about this co-kernel as a sheaf on spec R, if you prefer. Yes, though it is maybe not very clever to speak about sheaves here, because after all, spec R is an affine scheme, so I prefer to speak about modules. And so the reformulation, any module over a principal ideal domain is the direct sum of principal modules, each being generated by one element. This is the classical theorem. It shows that over a principal ideal domain, modules are very, very simple. Here they are. These are all the modules. Yes, and usually people study modules over non-principal ideal domain. And just one corollary, yes, which again is classical, and for example, Grothendieck proved it, the description of coherent sheaves on P1 over a field. Yes, so if F is a coherent sheaf, then necessarily it is the direct sum of these twisting sheaves and maybe some torsion. And so once again, this theorem, it follows from, it is more or less equivalent to Birkhoff factorization, and once again it follows from Smith normal form. So this shows that the Smith normal form is highly useful, and it is useful also in many other areas of mathematics. And now the problem is that most rings are not principal ideal domains. Yes? Even if you work with a ring of polynomials or a ring of formal power series, and there are at least two variables, then it is not a principal ideal domain. Yes, and therefore there is no Smith normal form. The moment you are in dimension bigger than 1, there is no Smith normal form. And here is this stupid example. Take just the matrix of indeterminates. Yes, suppose your ring is the ring of formal power series.
Dmitry, I have a question.
Yes.
What happens for dimension 1 when the ring is normal? So, for instance, you have a Dedekind domain. Is there some result in these directions?
For Dedekind domain, I think there is a Smith normal form. So once again, I'm not sure, but as far when it is one-dimensional and regular or correspond to a smooth variety, then there is Smith normal form.
And another comment is what you say for the projective line is that the corollary implies that every vector bundle is the direct sums of line bundles, right?
Exactly. This is the classical theorem of Grothendieck, right?
Thanks.
Yes. Yes. So once again, the problem is that in most cases of interest, there is no Smith normal form. Yes. So for example, here take this ring, take this matrix of indeterminates, and then the determinant here it is, and it is just irreducible. Yes, we cannot break it into pieces. And as the determinant is irreducible, there is no hope to bring this matrix to something, to a diagonal matrix. Yes, not even to upper triangle matrix, but because the determinant is irreducible. Now about the Dedekind rings and others. So in 50s and 70s, there was serious activity to characterize rings where Smith normal form exists. Yes. So you don't need PID. There are other rings. There is a broader class of rings where Smith normal form exists. Yes, where you can always achieve diagonal reduction. And such rings are called elementary divisor rings. But still, they are all close relatives. And they are all, in some sense, of dimension 1. So this is the essential part. The moment you are in dimension bigger than 1, you cannot diagonalize your matrix. So they all correspond to an affine line, to an open subset of an affine line, or to germ of an affine line, not more. And then the question is, so what to do when the dimension is bigger than 1? And we have just seen here that there are many matrices which cannot be block diagonalized. So what to do here? Well, let's start with square matrix case. So once again, this is the silly observation. If a matrix is left-right equivalent to the block diagonal, then the determinant must factorize. Yes. Therefore, most matrices will not be equivalent to block diagonal because the determinant is irreducible. Yeah, so the minimal necessary condition is the reducibility of determinant. Let's state it in for rectangular matrices, not necessarily square. So there, instead of determinant, you take the ideal of maximal minors. Yes, this is the classical ideal generated by all the m by m minors of the matrix. And then if A is equivalent to a block diagonal, then of course the ideal of maximal minors will be just the product of the corresponding ideals. Therefore, the necessary condition for block diagonalization is the factorization of this ideal of maximal minors. So let's fix the definition. So suppose the ideal of maximal minors factorizes, then A is called Ji decomposable. Yes, if A is left-right equivalent to the block diagonal form. Yes, and the ideals of these blocks are exactly this Ji. Yes, so this decomposition is corresponds to this factorization. So this is what we would like to achieve, and we would like to give some conditions when this is possible. Now, just a reformulation in terms of modules. So take a matrix, take the corresponding module. This is an R module. Yes, and then this ideal of maximal minors, it is just the zeros fitting ideal of the corresponding module. Yes, geometrically it defines the support of the module, where the module lives. And then the definition for in the language of modules. So we have a module over R, and we take its support. Yes, this is fitting ideal, its support. Suppose the support is decomposable. Yes, it consists of several irreducible components. And then M is called Ji decomposable if it decomposes accordingly to this decomposition. So maybe I should have drawn here some picture. Yes, but just imagine two lines. So support of the module is two lines. And then the question whether it's the module splits into something supported on one line and something supported on the other line. Whether we can decompose in this way. Now, the relation of the two definitions, yes, so fact, if a matrix is decomposable, then of course the module is decomposable. And vice versa, the inverse holds over local rings. Yes, if R is a local ring, then the module decomposable means that the matrix is decomposable. This follows just by uniqueness of minimal resolution over a local ring. Actually, you can also assume here graded ring. And if the ring is not local, then the composability of the module only implies that A is stably decomposable. So if you add to A, yes, you form the block diagonal sum of A with the unit matrix, and this will be equivalent to the block diagonal sum here. But usually in singularity theory, we work with local rings, so maybe this is not of much interest. So any questions? I will be glad to answer. Good. If there are no questions, so let's proceed. So let's take some simple examples. Here it is. So just yes, I'm online. Okay. So here is a very simple matrix, 2 by 2. Yes, this is the classical matrix in singularities and matrices, and also in commutative algebra. Its determinant is the classical singularity, yes, of type AK plus L minus 1. Yes, and therefore the co-kernel is the module over this plane curve singularity. Yes, this is among the simplest modules. Now we want this plane curve singularity to be reducible, to have two components. So we must assume that K plus L k plus L will be an even number. Yes, this is the necessary condition for decomposability. And then the question: so can we bring A by left-right equivalence to the block diagonal form? So in this case, block diagonal will mean just full diagonalization because the size is 2. Yes, so this is the question. Yes, and so what to do in this particular case? Well, now what can stand here on the diagonal, as we know that the determinant must be preserved. Yes, so this is the only thing that can stand on the diagonal. So once again, the question is whether A can be left-right diagonalized, yes, whether it can be brought to this matrix. Well, so probably this is the time to introduce or recall the determinantal ideals. We already used determinantal ideal of maximal minors, and here is the general. So IJA, yes, this is the ideal of all the j by j minors. And then j runs from 0 to m, and we get all the possible determinantal ideals. When we speak about 0 by 0 minors, then this is just the whole ring. And then the ideals decrease and decrease, and this is the ideal of maximal minors. And then we reach just 0, because there are no minors of size m plus 1. And all these ideals, they are invariant under left and right equivalence. They put invariance here. And now the theorem. Yes, for simplicity, I stated for square matrices and for the local ring. So suppose the determinant factorizes into the product of two elements. Suppose they both are co-prime, yes, and they are not zero divisors. Yes, the ring is arbitrary local ring, so it could contain zero divisors, but suppose these are regular elements. Then A is decomposable if and only if the ideal of almost maximal minors, yes, these are almost maximal minors, it should sit inside F1, F2. This is the ideal generated by the two elements. Yes, this is very simple, necessary, and sufficient criterion. So let's see how does it work in this particular case. So here, let's compute the ideal of almost maximal minors. It is just I1. Yes, it is generated by the entries of the matrix. Yes, so just these two elements, and then of course it can be presented in this way. Here I assume that number 2 is invertible in our base field. Yes, so this is the I1, this is the ideal, and now we should check that this ideal sits inside the ideal generated by one second, by what? No. Oops, I'm sorry. It should be not this matrix. I take I1 of this matrix. So we have here, this is the ideal, and it should sit inside this ideal. So this is the necessary and sufficient condition, and it holds if and only if k equal to L. So once again, this matrix, it admits the diagonal reduction only in the special case k equal to L. This is a very special module. It's very well known in the theory of modules over plane curve singularities. Only in this case we can bring A to the diagonal form.
Dmitry, I have questions. I'm sorry if the question is stupid, but yes. The determinant is always the product of two elements. For instance, you can take something irreducible times something invertible.
But invertible is, if it is invertible, then the diagonalization will be trivial. You will have a block of zero size.
So you eliminate this case in some sense.
Yes, certainly. So when I say coprime, I mean that they are not invertible. Yes,
Okay.
They are not units.
Thanks.
So this is
Dmitry,
yes.
can you extend this to 2 by n matrices?
So wait, this theorem is for square matrices. Yes, you ask about rectangular. There is corresponding statement, but it is more technical.
Okay.
I will address it later. Yes, currently for simplicity, I work only with square matrices.
Thank you.
So let's take just a little bit more general example. So let's take once again 2 by 2 matrix are a local ring. Yes, and suppose the determinant factorizes. Once again, co-prime, not zero divisors, not units. And then we get that A is decomposable if and only if the ideal of almost maximal minors. So it is generated just by the entries of the matrix, and it must sit inside this F1, F2. Yes, once again, very simple criterion. Yes, and in general, this condition is relatively simple to verify, both theoretically or computationally. Usually it is much simpler than to check that somehow you can block-diagonalize the matrix. So once again, here is this statement. Now, what is the geometry here? Yes, we have a module, once again, of projective dimension 1, because the matrix is square, or if you wish, a coherent sheaf on spec. And the support of this module is reducible. Yes, there are 2 components for the support of this module. They are hypersurfaces, yes, because we assume that F1 and F2 are not units, yes, and they have no common component. This is the meaning of coprime. And then if the first fitting ideal of M sits inside this ideal, then the module or the sheaf splits into the direct sum of 2 sheaves. Each is supported on the corresponding hypersurface. So this is the geometrical formulation of this theorem. Now, just one corollary there. Of course, you can get many corollaries, but here is just one. So suppose you work in dimension 2. Yes, here is the ring of formal power series in just 2 variables. Take the maximal ideal. Now we can always assume that the matrix vanishes at the origin, so its entries belong to the maximal ideal. Now, if this happens, then the determinant will be of order at least n. Yes, because every entry belongs to the first power of maximal ideal. Now, suppose the determinant factorizes, and suppose the curve germs, yes, these 2 curve germs in our plane have no common tangents. They could be singular, yes, but I want that their tangent cones will be disjoint. And now suppose that the order of the determinant is not big or equal, but equals exactly to n. So this is the generic case. There are no hidden degeneracies, no sudden cancellations. Yes, the order of determinant is exactly as we would expect. And then we get that the kernel decomposes into the direct sum. Or if you wish, the corresponding matrix is decomposable, is block-diagonalizable. Now, this condition that the order of the determinant is n, yes, as one would expect, it is classically known. It has been used in various areas, and it has many different names. In the area of determinantal representations, the condition is called locally maximal determinantal representation. In commutative algebra, one says that the co-kernel, this module, is an Ulrich maximal module. Yes, and usually these are the modules which people study first. They are in some sense, they are the simplest ones, or the most important. Now, this was the local version. Yes, we worked over a local ring. There is a graded version, which is also important. So suppose the ring is graded. Yes, the direct sum of its homogeneous components. For example, ring of polynomials. Suppose the matrix is also graded. Yes, it means that each entry is homogeneous. The degrees of entries could differ, but they must be compatible in this sense. As the simplest case, you can take just homogeneous matrix, where the degrees of all the entries is the same. Then this co-kernel module, you can consider it, you can think about it as a coherent sheaf on proj R. Yes, not just as a module over R, but projectivize everything, and then you get the coherent sheaf. Later I will give an example, very explicit example of this. Now we have a very explicit presentation of this sheaf. Yes, once again, we consider the matrix as a morphism, but not of free modules, rather these modules. Yes, so we have the twisting sheaves, yes, because of these degrees. So this is the morphism of direct sum of twisting sheaves, and it presents the sheaf co-kernel. And this is the global on the projectivization of R. And now we can localize. Yes, after all, we have some projective scheme, for example, P2. Yes, and at each point of this P2, take some affine chart, yes, on P2 or Pn, and take some local coordinates there. And then we get the local version. Yes, previously A was graded, and it was over this R. And now we fixed some affine coordinates and localized, and we have the local version over the localized version. And then we can ask for about the decomposability of this localized version, yes, or the decomposability of the initial version. Yes, so the decomposability of the sheaf of the global sheaf over the whole proj R, or the decomposability of the local objects, point by point. So here's the statement. Again, for simplicity, it's for square matrices. So once again, suppose that this sheaf is supported on two components, and they are hypersurfaces, and they intersect properly in the sense that they have no common component. And there's some technical assumption that I will state later. Then the following are equivalent. The sheaf decomposes globally into the part supported on one hypersurface plus the part supported on the other hypersurface. Or each stock of this sheaf is locally decomposable. Yes, already on the projectivization. Or once again, the ideal of almost maximal minors on the local sits inside this ideal local. Yes, this is locally. So this is the theorem. It is sort of graded to local transition. Yes, so once again, we wanted to decompose A over the ring R. Yes, and this is a graded question in this dimension, or if you wish, it is a global question on proj R. And this statement, it reduces the global question to many local questions. So maybe this was a bit abstract. Let's see some example. First, this technical assumption is the assumption. So we assume that the depth of this quotient is bigger than 0. Yes, geometrically it means that there exists a hypersurface that intersects properly both this hypersurface and this sub-scheme of codimension 2. So this is the full statement now, and let's see the example. This is the simplest possible. So let's take the ring of just polynomials in 3 variables, and suppose A is a homogeneous matrix. Yes, all the entries are homogeneous in these 3 variables of the same degree. And then the co-kernel is a sheaf on the determinantal curve. the determinant of this A will be some homogeneous polynomial. It will define the curve in our plane, in the projective plane. And the co-kernel of the matrix lives on this curve. And now suppose this curve decomposes. Yes, it has two parts. Maybe C1 is further decomposable, but we assume that it decomposes at least this way, and that C1 and C2 have no common components. So they intersect in a finite number of points, yes, globally on the projective plane. Then the statement is that the global sheaf, yes, supported on this union decomposes if and only if all its stocks at all the intersection points decompose. So again, this is the global object. It is supported on the projective curve. So this is the global question. And somewhat surprisingly, it is totally reduced to the local questions. Yes, there is finite number of intersection points, and at each point we should check the composability. And of course, the composability locally here, it is a question in two variables. It is much simpler than the composability here, yes, over this ring, which is the question in three variables. Now, this result is a bit surprising because one could expect monodromies. If we check the composability at each intersection point, yes, maybe as we go from one point to the other, yes, and do some loop, maybe there will be a monodromy and it will obstruct the global decomposability. But the statement says that there is no monodromy here in this case. So this is the graded version. Yes, this reminds, of course, of the Noether fundamental theorem when you want to check that some polynomial belongs to the ideal of two other polynomials. So this is sort of matrix version of Noether's theorem, is AF plus BG. Well, so any questions? I guess I have time, so I will be happy to answer questions. Well, just to check, I'm online, okay. So if there are no questions, let's proceed. So some remarks and applications. So once again, there were two main theorems. This is the graded to local transition and the previous theorem, and now let's see some remarks and applications. So until now, I worked only with square matrices. Yes, they are the simplest, of course. The results extend to rectangular case when the matrices are not square, but then we have technicalities. They are really commutative algebra enters, and there are some local cohomologies and so on and so on. Now, until now, the equivalence was left-right. Yes, U, A, V minus 1. Usually for square matrices, one wants U, A, U minus 1. Yes, the conjugation, the traditional conjugation of linear algebra, which is so useful in various areas of mathematics. And it so happens that the conjugation, the problem for conjugation is embedded into the left-right. Yes, you should just extend your ring. Yes, introduce a new formal variable. Let's extend by t. And then there's some elementary observation that two matrices are conjugate if and only if these matrices are left-right equivalent. Here one is the unit matrix, and so if this is left-right equivalent to this, then of course the V must be Q. Yes. So this is some silly observation, and it means that if you want to check the block diagonalization by conjugation, you can do it for left-right equivalence just over a larger ring. Yes, so here is the corollary. Suppose the characteristic polynomial factorizes, yes, of this matrix. Here is the characteristic polynomial, factorizes now in this ring. and F1, F2 are again co-prime, then A can be block-diagonalized by conjugation. So I don't know why it is written namely, just then, it should be then. Can be block-diagonalized by conjugation if and only if this ideal of maximal minors sits inside F1, F2. So usually when you add some variable, you get a question in larger number of variables, and usually such questions are harder. Yes. So this observation usually does not help. But in our particular case, the criterion it is blind to the complexity of the ring. So it doesn't matter how many variables you have, you should just check this condition. So maybe let's return to the initial example. We have the same matrix, and now we want to diagonalize it not by left-right equivalence, but by conjugation. So let's see. We compute a characteristic polynomial. Here it is. Yes. Once again, we have to assume that k plus l is an even number. And then we compare the ideal of almost maximal minors. So just in this case, it is the ideal of all the entries to the ideal of F1 and F2. Here is this ideal. Yes, and the conclusion is that A is diagonalizable by conjugation if and only if k equals to L. So previously we have seen that in this case, A is diagonalizable by left-right equivalence, actually even by conjugation. Well, and now some applications. So let's start with application to operator theory. The traditional question there is if we are given a set of matrices over a field. Yes, here are matrices of constants. When can these matrices be simultaneously something? For example, diagonalized or brought to some particular form. This set can be finite or infinite, even uncountable. And this is the old classical question. It was studied for many years, and various criteria were given. Yes, for example, the simplest criterion is the matrices can be simultaneously diagonalized if and only if they all commute, as we know. But sometimes this criterion is not good for some applications, and people needed other criteria. Yes, so let's see how can we answer this question. Well, instead of many matrices, we'll consider just one matrix. We introduce formal variables, and we collect all these matrices into just one matrix. Just now, it is a matrix not over a field, over a ring. Yes, this is not a constant matrix. It is a matrix of polynomials, maybe infinite number of variables. Depends on how many matrices there are. And then the necessary condition is, of course, that the determinant factorizes. And as always, assume that these two factors are co-prime. This is some minimal genericity assumption. And then these matrices can be simultaneously left-right, simultaneously block diagonalized by left-right equivalence, if and only if the same, the ideal of almost maximal minors sits inside F1, F2. So this is an answer to some old question. Yes, previously this question was studied in the framework of operator theory or linear algebra, and of course they never considered such approach. Yes, their criteria were completely different, of different style. Now, if we want to block diagonalize by conjugation, not just left-right equivalence, then instead of this matrix, take this matrix, add one more variable, and we will get a similar criteria. Now another application to representation theory. So take some group or some algebra and take a finite dimensional representation. Yes, as always, in Lie groups and Lie algebras. Yes, here I fixed some bases. So instead of GLV, I consider very explicit just matrices. So then the image of this group or the image of this algebra is just a set of matrices. Maybe infinite, maybe uncountable, but just set of matrices. And then if you ask whether the representation is decomposable, it means that all these matrices can be simultaneously block-diagonalizable. Yes, by conjugation now, not by left-right equivalence, by conjugation. And now this is very easy to verify. Here is the criterion. So at least in each particular case, you just check that one ideal sits inside the other. And just mention in the same way one can treat the congruence, UAU transpose. This is important for skew-symmetric matrices or quadratic forms. And more generally, one can get the decomposition criterion for quiver representations and many others. Well, so let's go back to the first statement. Yes, the first theorem. Yes, I wanted just to see the geometry of the assumptions. So once again, A is F1, F2 decomposable if and only if this ideal of almost maximal minor sits inside this ideal. Now the meaning of the assumptions. What is this assumption? So let's see. The locus, the determinantal locus is exactly the locus of points where the matrix is degenerate. Yes, where the rank is smaller than n. And this locus, yes, almost the determinantal locus, is the locus of points where the rank is smaller than n minus 1, or co-rank is at least 2. And therefore, this condition means geometrically co-rank is bigger or equal than 2 at the points of F1, the intersection. That's when the two components intersect, the co-rank must drop. And this is quite expectable. Now just a bit about the proof. Oh, I'm quite ahead of time. So the proof, first of all, there is a reduction to the case R is local and Henzelian. Yes, for example, Henzelian formal power series or local analytic series. And it uses some commutative algebra, uses some local cohomologies. And then once we reached that the ring is local and Henzelian, one uses just linear algebra over a ring. Yes, as in classical linear algebra, one has linear algebra over a field, and here it is linear algebra over a ring. And the proof is not so long. It takes a couple of pages. Well, and that's it. Nobody asked questions, so I finished earlier. Hopefully you do not object. So thanks for your attention.